for diagonalization, and this method and its different modifications are very useful for proving such theorems. But before we start with diagonalization, let me give some formal motivation for why should we study time hierarchies. Okay, good. Just to motivate the study of time hierarchies, let us consider the problem of matrix multiplication. So you have two matrices, you have to compute the third matrix, and so the question is, what is the time complexity of this problem? And it's fairly easy to come up with an algorithm that computes the product of two matrices and does it in...
complexity is just the number of arithmetic operations.
Yeah.
Okay.
Yeah. So this is just motivation. This talk has nothing to do with matrix multiplication. Okay, so there are less naive methods. For example, it took some years to come up with a method that is faster than n to the 3, and Strassen was the first to give such a method. There was a line of improvements, and finally we have an algorithm that runs in time n to the 2.38. Well, it's what we have. On the other side, we have lower bounds, something like no one is able to compute the product of two matrices in time less than n squared, just because you have to spend time n squared to read two matrices. And the question is, if you have to choose between these two bounds, what seems more plausible? And some people may say, well, n to the 2.38 is too unnatural, so maybe it's the wrong answer. Okay, so is that time bound too strange? And what time hierarchies tell us is that such time bounds are not too strange, because for any real k, there are some artificial problems that can be solved in time n to the k plus epsilon, but can be solved in time n to the k. This is why such time bounds do not look too strange. Okay, and we know that time hierarchy exists for deterministic algorithms. But there is an open question. So if we switch from deterministic algorithms to probabilistic ones, and we start to we ask the same question: is time complexity like n to the 2.38 too strange for probabilistic algorithms? Well, the question is open. We don't know. We don't know whether time hierarchy exists for probabilistic algorithms. And as we don't have any answer to this question, one may try to start asking similar questions that may be a little bit easier than this one. And there are several such questions. For example, one may start to ask, are there time hierarchies for non-deterministic algorithms, non-deterministic algorithms, and many other kinds of algorithms? Also, we may ask the question, are there time hierarchies for probabilistic heuristics? And also we may ask, are there time hierarchies for probabilistic non-uniform algorithms? Today I'm going to speak about these questions, and actually I'm going to speak about the method that is used for obtaining answers for these questions. And this method is diagonalization. But I would like to start with, not with time hierarchies, but with the theorem that real numbers are, the set of all real numbers is non-countable. And I believe that most people here studied this theorem in analysis, so let me just review its proof. I would like to review the proof of this fact because it was the first use of diagonalization. And in 1874, Cantor has to invent this method, the diagonal argument, in order to rigorously show that the set of all real numbers is non-countable. So let us follow his steps. it would be more convenient to work with the set, not with the set of all real numbers, but with the set S of all infinite strings over a binary alphabet. One may see that there is a bijection between these two sets, between the set of all real numbers and the set of all infinite string over a binary alphabet. So let us show that S is non-countable, and this would imply that the set of all real numbers is non-countable. For that, assume that...
But maybe we can just look at for a while at the picture and
good.
Switch to the next slide.
Okay.
I think everybody can provide the sound for this
yeah, sure.
video. Yeah. Okay. Just have a lot of questions for you at the end. So.
Okay. Tell me when.
Yeah. Okay.
Okay.
Just do as you would ignore him. And Vershegen too.
And some other people. Okay, just move on.
Okay. So just to summarize what we have seen on this slide, what we have learned from this slide is that if we assume that S is countable, well, then we can construct another string that doesn't belong to this set, okay? Because T differs from Si in position I, in character I. So T doesn't belong to S, but on the other hand, it should belong to S by definition, because S is the set of all infinite strings. And so we have proven that the set of all real numbers is non-countable. Okay, so we see that it's a fairly simple argument, and surprisingly, this argument that was invented to do some things in the foundations of mathematics can be applied to some things that are in the foundation of complexity theory. The first use of diagonal method in complexity theory is the proof of time hierarchy for deterministic algorithms. Okay? And actually, it's one of the very first theorem in the field. It was proven in 1965. So let me switch to this theorem. First of all, I have to say that it's much more easier to work with languages rather than with functions. So in the mathematical part, we had matrix multiplication. It was a function from two. We have two matrices. We have to compute another one. But now let us consider those functions that output either 1 or 0. So we are going to work with predicate functions, or equivalently with languages. Let me make one definition. So I would like to introduce this class of languages. It's the class of languages that are recognizable in time and to decay by deterministic algorithms. And now what time hierarchy tells us is that there is some language that is recognizable in time and to decay plus epsilon, but is not recognizable in time and to decay. Okay? And in order to prove this theorem, it's enough to construct a language that belongs to this class, but is not in this class. Okay? And to do this, we are going to use the idea of counter. Okay? Let us see how we do this. First of all, let us learn how to write down a language. So, consider a characteristic function of a language L. This function receives arguments in the set of all strings, all finite strings, but alternatively we may think that it receives arguments from natural numbers. So we take language L and just consider its predicate function and write down its value on 1, on 2, on 3, on 4, and so on. Now, let me enumerate the class of languages recognizable in time and to decay. It's certainly enumerable just because the set of all Turing machines is enumerable. Okay? And we write down these languages one by one. Okay? And consider the diagonal, and consider a language L that differs from any language in the set the time and to decay. So obviously language L is not recognizable in time and to decay. What remains to be done is to show that this language can be recognized in a little bit more time and to decay plus epsilon. Again, I believe that most people here know this proof. So just to remind you, what we do is we take a nice enumeration of languages it's more convenient to enumerate Turing machines, okay, and then just take the languages that are recognizable by those machines. Okay, so we enumerate all Turing machines that run in time n to the k. For that, we can just enumerate all Turing machines and then restrict them to run in time n to the k. Okay? And now I construct a new machine B that on input I takes machine A sub I, simulates it on input I, and returns the opposite answer. Okay? One may see that actually B recognizes the language from the previous slide, and also we may see that B runs in time n to the k plus epsilon. The most complex step is to simulate AI. It takes time n to the k, and we have some overhead for simulation. Okay? So we're done. Are there any questions? No. Okay, but okay. Actually, it's much more easier to think about this without any diagonals. So just to sum up, what we have done is we have constructed machine B that disagrees with any machine AI that runs in time n to the k. Disagrees, I mean that on some input they produce different answers. And also B is n to the k plus epsilon time machine. Okay, so the proof is fairly easy. Okay, let's get to a little bit more complex things. The second use of diagonalization in complexity theory is the time hierarchy for non-deterministic algorithms. And though the time hierarchy for deterministic algorithms was one of the first theorems in the field, it took several years to prove this result. And in 1971, Hooke was able to come up with the proof that non-deterministic algorithms have time hierarchy. It took some more time in order to simplify the proof, and finally in 1983 some people realized that it's possible to prove this theorem by an extension of diagonalization. Okay? Let us see how we do this. Again, let me introduce a new class of languages. Those are languages that are recognizable in non-deterministic time by non-deterministic algorithms in time n to the k. And what time hierarchy tells us is that there is some language recognizable in polynomial time by non-deterministic machines, but not recognizable in linear time by non-deterministic machines. Okay? It's somewhat simplistic theorem. Actually, the real time hierarchy is more dense, so there are languages between n to the k and n to the k plus epsilon, but for simplicity, let us prove this statement. Okay. The first idea is certainly to try to use the standard method, the diagonalization that we used for deterministic algorithms. So let us see, maybe it works. Okay, so if you remember, we constructed machine B, and we defined it on input X in the way that it simulates AI on the same input and outputs the opposite answer. Why can't we do it for non-deterministic computations? Well, now AI is non-deterministic. And this means that we don't know how to simulate it and output the opposite answer efficiently. If we knew, then this would imply that NP is equal to co-NP. So it's not possible to do it efficiently. And so this is why that simple idea doesn't work. So now let us see how we can fight this problem. And the trick is called delayed diagonalization. Okay, so instead of one input, so I want to teach machine B to disagree with machine AI. So for that, let me choose a number of different inputs. Let xk be a string of length k that consists of zeros only. And I take a big number of such strings, xn plus 1, x2 to the n. So this is a string of length n, and this is a string of length 2 to the n. Okay, now what we do is we define B in a way that on the longest input, it simulates AI on the smallest input and outputs the opposite answer. Okay, so the trick here is that, well, although we cannot efficiently negate the answer of machine AI, we still can do it inefficiently in exponential time. And if you see, AI is linear time, the length of xn is n, so we need time 2 to the n in order to negate the answer of AI. And actually b is given input of exponential length. So b can negate AI on input xn and still be a polynomial time machine. Okay? So this is a trick. And somehow we want to make b compute this value on the smallest input. And then we will obtain a contradiction. So we'll get b disagreeing with AI. So another trick is to construct b, to define b on other inputs in the way that on input xk minus 1 it simulates AI on input xk. Okay? And now, in the beginning of the proof, we may assume that AI agrees with b everywhere. Okay? So we assume that polynomial time doesn't give us ability to solve any new problems. So some AI agrees with b. But this means that AI on input xk outputs the same answer as b on input xk. Together these two equations give us this equation. So b on input xk minus 1 outputs the same answer as it does on input xk. Okay? Good. And now, from this and this, we get that b on input xn, b on the smallest on the shortest input, outputs answer that is opposite to the answer given by AI on the same input. And this obviously means that b disagrees with AI, and we have a time hierarchy theorem. So, if there are
so we don't need any fixed point thing. Just
no.
We
just have constructed b that disagrees with AI. But we have to assume that some AI agrees with b, and then
But somehow I missed the point. How do
the point is to
what is this relating language is b, right?
So we want to
check
construct b which differs from AI, yeah?
Yeah.
But we do not bother now b in n time of something.
No, we want b in n time, but we deal only with one AI, just in this picture.
It's just a part of the picture. We also have inputs for AI plus 1.
But assume we won't just diagonalize against a specific AI somewhere. Okay, and what do we do?
I show that at least on some of these inputs, b disagrees with the AI. But I don't know at what.
This is the definition of b.
Yeah, this is the definition of b.
Okay.
No, definition is this line is a definition.
This one
and this line is definition.
Yeah.
And this line is not a definition. It's just.
But somehow that line contradicts to that line. It might contradict at least. Why not?
First, this is a definition.
Okay.
b of long string, and for shorter string, this is the definition. And if it happens that AI coincides with b
everywhere,
then we have this line, middle line, and together with this line, we get what we want.
So we have this line and this line for every k from n to the n. And by transitivity, we'll get that b on xn is equal to b on xn plus 1, it's equal to b on xn plus 2, it's equal to b on x to the n. And this is exactly what we wanted to compute. Okay. So, any more questions?
No, there is some global question, but let's postpone it.
So you need a sequence 2 to the power 2 to the power k. To make this definition correct, you need such a sequence.
Yeah, so we have spent a lot of length for one for one to deal with one
The
AI.
definitions work on between xn and x to the n.
Between n and 2 to the power n, there are some other powers of 2. Between 5 and 32, we have 16.
Yeah. But we deal only with one, and then we use the next for next machine. So it grows fast. Yeah, no problem.
We do not need to use every power of
No, n has
N
has nothing to do with I. It's a different letter. Machine AI is some part of the line is allocated for it, and for next AI will be the next part of it.
Okay, most of inputs are not used. On them we may define the arbitrary. Okay, so I select some
It's
special.
not, but the question.
I see no difficulties, but
So what is your
as I
question?
understand, to make this definition correct, you should use n in the form of power 2. N should be
No, I mean,
power n.
okay, if I want to diagonalize against a sub I plus 1, I'll take x to the length 2 to the n plus 1, 2 to the... So I will not use any...
We don't understand the
Look,
question.
n
So
does not coincide with I.
Yeah, there's no correspondence.
There is, but it grows very.
just say something else if you want to get an answer, because now nobody understands what you are saying.
Maybe I can answer afterwards.
Actually
But
understood the question.
Okay, but let's continue.
But
because
for now, just important, but we have now B is able to disagree with AI. Okay. And now we turn to some more recent results on time hierarchies.
So one more question about the previous
Yeah,
slide.
sure.
Whose proof is that?
Jacques, Stanislav Jacques,
And of which year?
1993.
Okay, thank you.
Okay.
and before it was something.
Cook. Yeah, I knew another one by
This is
Cook.
much nicer than
Yeah.
Yeah, there is
This
Cook.
is very simple.
Yeah, very simple.
Yes, there is also Cook and there is also Cephas Fischer-Meyer.
Much more complex.
But they, in some sense, they assume that NP is equal to n time of n, and then they derive stronger and stronger implications. They do not construct machines. But it's very simple, and we'll use this delayed generalization to get to more results. Okay. So now let us turn to heuristics. And I'm going to show how to prove time hierarchies for heuristics. It's a little bit more complicated than those things that we have seen on the previous slides. So let me define what I mean by heuristic. Well, roughly speaking, we'll say that some algorithm is 90% heuristic for some problem if this algorithm solves 90% instances of that problem. Okay, so it's quite reasonable.
Or given length, for example.
Yeah, but for now it's just roughly. Okay, and good news is that although we don't know whether time hierarchy exists for probabilistic algorithms, nevertheless we know that time hierarchy exists for probabilistic heuristics. And I think it's a very nice result. But today we're going to speak about a related result that's about time hierarchy for heuristic non-deterministic algorithms. So, again, I introduce one more class of languages just to make things more precise. Okay, so this class, and language L belongs to this class if there exists some n to the k time non-deterministic machine that such that the following line holds. This means that machine AI recognizes, correctly computes the predicate L on at least 1 minus delta fraction of all inputs of every length n. So let me just give you a few seconds to read this.
So correctly means that if it's lucky, it produces a correct answer, And if it's unlucky, it doesn't produce any answer.
Okay, on the remaining delta fraction of inputs, we allow AI to produce wrong answer, not to start.
But of course, but for the correct part of inputs, what does it mean that AI non-deterministically produce L?
This means that
there is a way to produce it.
Yeah,
there is no way to produce incorrect answer.
Right.
Yeah.
Right.
Is it involved in that definition?
Yeah, AI, if X equals to something, what does it mean?
Okay.
It's not a predicate, it's just a function. So
where there is a function?
L of X.
L of X is just a function with two values, I guess. 0, 1?
Yeah.
No, but so that's the question, what you mean. So, is it symmetric or non-symmetric? If L is 0 or 1, it's more or less the same definition. Yeah.
L of X is just a function, okay?
Yeah.
Okay. What it means for non-deterministic AI to produce... okay.
Yeah.
What is AI of X? It's 1 if there exists a witness, and it's 0 if there is no witness.
Okay.
So this just means the answer of AI on some input.
Okay. It's how this should be understood.
So, for example, if the negation of L is not recognized automatically by this, not in this case. So it's non-symmetric.
Non-symmetric. And what? As usual NP?
So there could be different definitions, so I want just to fix one. So this is not symmetric. If language L has this property, the negation is not necessary, doesn't necessarily, at least not trivially have this property.
I believe yes. So what this definition says is that L belongs to this class if there is L in NP that significantly agrees with...
Then I understood the thing correctly first,
Okay, so we'll just try to digest the definition. If there are any questions, just feel free to ask. And now, we have the following theorem, which says that there exists a language recognizable in polynomial time by a non-deterministic machine, but is not recognizable in linear time by 1 minus delta non-deterministic heuristic.
For any delta, I guess. For any delta less than 1/2. It's important. It's no more than 1/2. Okay? So, on the one hand, this theorem is stronger than non-deterministic time hierarchy. If you remember, we had NP is not inside n time of n. But now, this result is somewhat stronger because now we have to construct language in NP that significantly disagrees on significant fraction of instances with any language that is recognizable in linear time. Also, we may see that it's somewhat stronger than simply a time hierarchy for heuristic algorithms, because on the left-hand side we have perfect algorithms, not just heuristics. Okay. So how would you prove this? Okay. So what we have to do in order to prove this theorem, we have to construct some machine B, polynomial time, non-deterministic machine, such that whatever non-deterministic linear time machine AI we consider, B and AI significantly disagree. They disagree on at least delta fraction of inputs of some length. Not just on one input, but they have to disagree on delta fraction of inputs of some length. Okay? And in order to do this, we'll construct B, then we will make an assumption that some AI agrees with B on 1 minus delta fraction of inputs of every length, and then we will derive a contradiction. Okay? Firstly, let me try delay diagonalization in order to prove this theorem. Maybe it works. So again, let me choose a number of different strings of different lengths, xn, x2 to the n. Again, we define machine B on input x2 to the n. Again, we define B on all other inputs so that it simulates AI on xk. And now we want to use a sum